Right, here's a pretty simple theorem to prove. Suppose f of x is differentiable at x equals c. Then f of x is continuous at x equals c. Differentiability at c implies continuity at c. Proof. So recall that x is continuous at x equals c if the limit as x goes to c of f of x equals f for c. Now, of course, you didn't have to write this, but it's not so bad. So, we need to take the limit of f of x and somehow get f for c, and it has to involve the derivative. So, start this thing. I have f of x, and somehow I want to build up the derivative. And remember, the derivative, or at least the difference quotient, is going to look like this. So I say, well, f of x is equal to itself. I want minus f for c. So it starts to look at the top, like the top. And then I add f for c. And I concentrate just on that. And I'm like, well, you know what? If x is not going to be c, then x minus c is not 0. That is, well, let me write this first. X minus c divided by x minus c is not 0. It's not 0. Sorry. It's not 0 over 0. Okay, so I just multiplied by 1. And let's not forget to add the c. Okay. So we now have that f of x is equal to that. So we look at their limit. The limit as x goes to c of f of x is equal to the limit as x goes to c of this, because that equals f of x. So it's f of x minus f for c over x minus c times x minus c plus f for c. We want the limit of all that, but the limit over sum is the sum of the limits. So we're just going to now apply a few of the limit rules, at least 2 of them. The limit of this term plus the limit of the second term, f for c. Now, the first limit, well, it's what's in the brackets times something else. That is the limit of our product. Oh, that's the product of the limits. That is, I can take the limit of the first factor, which is what I'm trying to write now. That's the limit of the first factor times the limit of the second factor, x minus c. Plus, let's not forget this lone limit at the end. Okay. Now, the limit of this, since f is differentiable at c, is f prime or c times, as x goes to c, x minus c goes to 0, plus f of any value, c or otherwise, is a constant. When we take f of a number, we get back a number, a constant. So this is a constant. As x changes, that constant doesn't. So this is equal to 0 plus f for c, which equals f for c. So in the end, I showed that this limit, it equals a lot of stuff that you see on the board, but in the end, it equals f for c. So f of x is continuous at x equals c. Now, I want to make one main big point. Anything times 0, especially when you're talking about limits, is not 0. It's not 0. For example, if this here was undefined, maybe it was 1 over 0. Okay, 1 over 0 times 0 is not 0. Okay, this value had to be well defined. It had to be well defined. Okay, f prime or c exists. If it equal to 1 over 0, it didn't exist. Okay, it wasn't well defined. It is no longer true that anything times 0 is 0. Anything well defined times 0 is 0. And f prime of a number is, if it's differentiable at that number, is a well-defined number, like 7 pi, 1 over e, pi over e, 2/3, negative 2/3. And when you multiply those numbers by 0, you do get 0. So we really, really needed for this limit to exist. That completes this proof. Thanks for watching.